Now you won't be surprised that by the very same technique one can show that not just R2 but also Rn is complete if you equip it with this standard Euclidean norm. But to be honest, it's not about the 2 norm. You could do the same argument for any other p, even for p equals infinity, and you would still, well, the proof would almost be the same. Okay, so this is Banach space. And we explicitly include the case p equals infinity. Now, having said that, it's clear that also the complex numbers with the standard modulus that you have in the complex numbers as a norm form a Banach space, because essentially you can identify them with R2 with the 2 norm, right? And the same proof works for infinite vectors, so you could look at LP spaces equipped with a P norm and do the very same thing, again including P equals infinity, and you will be able to see that this is also a Banach space. So completeness is again the critical criterion here. And the only challenge is to show that the limit that you achieve in the end is still inside your space LP or L infinity. But also that is not a big problem. So you can do that for each of these examples. And you can go even higher to spaces of functions like capital LP, let's say functions on an interval AB, and you equip them with that corresponding P norm, and by almost the same arguments show that, again, this is complete, and again that includes P equals infinity. You can also look at the space of continuous functions over an interval AB and equip that with the infinity norm. Let's do that on purpose. And you could show that this is complete. Also complete. So also here you work component-wise, or in this case you would say point-wise, and first show that for every point, little x, in the interval AB, the corresponding sequence is a Cauchy sequence in the real numbers. Then conclude from the completeness of the real numbers to the existence of that limit. And then glue all these limits one to another, which means this gives you the limit function. And then show that indeed your Cauchy function of continuous functions converges with respect to that infinity norm to this limit, and the limit is again continuous. So if your functions are f1, f2, and so on in the space of continuous functions AB, let me save those round brackets here, and you have convergence in this infinity norm, so you have fn minus f, infinity norm goes to 0, it remains to show that the function f is a continuous function. Now maybe we should try to understand that convergence better. If you spell it out, then it means that the supremum, or x in AB of modulus fnx minus f of x goes to 0 as n goes to, let me see that, as n goes to infinity. So let's spell that out even more precisely. So for every epsilon greater than 0, there exists n0 and n, such that for all n greater than n0, we have that the supremum of x in AB modulus fnx minus f of x is less than epsilon. And instead of saying supremum here, which is correct, but let's just replace it, you could say for all x in AB, the following is true. And if you look closely, then you see that this is exactly what you called uniform convergence. Uniform convergence of a sequence of functions in your Analysis 2 course. Speaking about uniform convergence, let's quickly recall the other kind of convergence of a sequence of functions that you've heard in Analysis 2. That was so-called pointwise convergence. For pointwise convergence, all you do is you move this for all x in AB quantor to a much earlier position, like here. I mean, you could also move it here. These two quantors are essentially the same, so you can commute them without changing the meaning. But if you did that, you would get pointwise convergence, and we could spell that out as for every x in AB, you have that fnx minus f of x goes to 0 as n goes to infinity. And if you think about it, then that is a lot weaker than what we said at the beginning, that the supremum goes to 0. There is this uniformness involved, which gives rise to the name uniform convergence. Okay, and that's the key, because if you remember your Analysis 2 course, then at some point you have learned that if you have a sequence of continuous functions and that converges uniformly, so this is our new shorthand for uniform convergence, then the limit will also be a continuous function, and that's what gives you completeness here. We should probably also look at some negative examples, so you don't think that every norm space is a Banach space. Well, maybe let's stick to the same example as in G, the space of all continuous functions over the interval from A to B, but now not with the infinity norm, but with, let's try the one norm. And I claim that now this is not complete. Okay, and here is my example. We take the interval from -1 to 1. And look at the following sequence of functions. So here is -1 over n, here is +1 over n, and the function fn is 0 between here, 1 between here, and linear from here to here. So it's a continuous function that crosses this axis at a half, arrives here at 1. Okay, and the interval AB is -1 to 1. So if that is your graph of the function fn, and you let n go to infinity, then I think we all agree that in the limit we expect a function with the following graph. So as n goes to infinity, you will see that 1 over n goes to 0. So the functions will become steeper and steeper around the origin. And in the limit you would get everything 0 here, everything 1 here, and okay, at point 0 maybe it stays at a half or so, but that 1 point is not so important. Let me just denote that limit by f. Now let's try to convince ourselves that this is indeed the limit. So we have to do the computation. So I'm claiming that fn goes to f in one norm. And to show this, you have to compute the difference fn minus f in the one norm, which is the integral from a to b, which is minus 1 to 1 of modulus fn x minus f of x to the power 1 dx. So in the end, if you look at this difference, then you could, for example, just copy the graph of f into the first image, which would give you something like this. And then look at the difference between blue and red, which gives you this this bit here. And your integral is computing exactly the area that I was just drawing. Right? I mean, you're integrating this difference, and that would just give you the area that I just shaded out, which must be, okay, we just have to compute the area of triangles. So what is that? That is 1 over n times a half divided by a half. That's the size of one of these triangles, but then you have two of them, which gives you this, which if you summarize is just 1 over 2n, and that indeed goes to 0 as n goes to infinity. So yes, it is convergence in the sense of this norm. However, you will clearly observe that the limit is not a continuous function. So if we try to draw this here, then we are maybe inside L1 of AB, and we look at the continuous functions in this. And our sequence, so maybe f1 is clearly a continuous function, and f2 also, and so on. But then I think we can all agree that this limit is no longer a continuous function. So it happens that the limit of our sequence is outside the continuous functions, and that means we have a convergent sequence here, which converges in the sense of L1, because what we saw in the one norm, but the limit is outside our set of continuous functions. And what's this telling us is that our set of continuous functions is not closed. Okay, well, if you forgot, then quickly recall the definition of a closed set, and then you will agree. And while you are recalling, you will see that completeness implies closedness, or non-closedness implies non-completeness. But if it's not complete, then it's not a Banach space. Right, so this was our first negative example. Note that the situation does not change if we replace the one norm here by any other p norm with p less than infinity. I mean, what would happen if this were p with p less than infinity? Then we would just take pth powers here, and this means you're taking the pth power of all of these vertical distances, which are obviously all less than 1, between 0 and 1. Now taking them to the pth power only makes them smaller because b is bigger than 1. So that would make the whole integral smaller, okay? So we would get less than or equal to sign here. Now let's not forget about the pth root, that of course also belongs to the p norm that we should write here and here. So we get pth root sitting here, and then also here and here. But of course we still agree with the result because p is not moving, but n is going to infinity, and then still this term's going to 0. So also with the p norm, p less than infinity, we have the same example of a sequence of continuous functions converging to a discontinuous function, showing that the space of continuous functions is not closed, hence not complete, hence not a Banach space when equipped with the p norm p less than infinity. The situation changes when you take p equal to infinity. We mentioned that before, then it becomes a Banach space, so it is complete. So how is that example not working there? Well, we could check what the infinity norm of our difference fn minus f is doing. By definition, this is just the supremum with x running over our interval, which is minus 1 to 1, and we have to look at the difference of fnx minus f of x. No matter how large your n or how steep this graph fn is around 0, there will always be points x close to 0, where this vertical distance between fn and f is as close as you want to a half, but not bigger than a half. So one can see that the supremum will always stick at a half, and therefore obviously not converge to 0 as n goes to infinity. So that's why this example is just not a counterexample if you take p equal to infinity. It's just not convergent to this discontinuous function. So to give you one further example for non-closeness, let us look at the sequence space that we denote by C2-11. So remember that is the space of all sequences with only finitely many non-zero entries, and we usually equip it with the infinity norm. Then you will see that it's not closed. So for example, let me take the first element, which is the sequence, maybe 1, and then all the rest zeros. The second is 1.5, and then all the rest is 0. Third is 1.5, a third, and then all the rest zeros. So the end element in that sequence, the elements of which are again sequences, would be like this, and then you have zeros all the way. So each one of these is an element of C00 because each one of them only has finitely many non-zero entries. However, you can easily show that this sequence converges uniformly, as we say also in the sequence world, to the sequence x, which is 1.5, a third, 1/4, and so on. No zeros in this sequence, only 1/n's running with n over the integers. If you're wondering why this is so, well, you can just compute it. You can just check the difference. So you would compute x minus xn in the infinity norm. And if you take x minus xn, then you will see that the first n entries of your sequence are 0, and then you get 1/n plus 1, 1 over n plus 2, and so on. And you have to compute the infinity norm of this. And recall what the infinity norm is. It is the maximum or the supremum of all the entries, and that will clearly be here. So this is 1 over n plus 1. So indeed this goes to 0 as n goes to infinity. So what did we just observe? We observed that we have a sequence in C00 that converges, but the limit is not in C00 because it has infinitely many non-zero entries. So again, we have a situation that, where am I drawing this? Inside of L infinity, we have this C00, and we just gave an example of a sequence x1, x2, x3, and so on, which converges to a limit that is outside. Okay, so this x was here, and all the x1s, x2s, and so on have been inside of C00. So again, like in the previous example of a non-Banach space, this one here is not closed, therefore not complete, so it's not a Banach space. Okay. Maybe you remember that if a set is not closed, you could still pass to its so-called closure. The closure of a set is just the smallest set surrounding the set that is closed. So you would look at something a little bit bigger than C00. Maybe this here. Would definitely contain that limit, because that's the job of the closure. So let me write the closure of C00 here. And it's actually not too difficult to show that this is exactly what we denoted by C0. It's the set of all null sequences. So these are sequences that converge and go to 0. So in particular, we can see that this set is now closed. And because it is contained inside a complete space, L infinity, we saw that before, we can even conclude that it is complete and therefore a Banach space. Okay.